This is C2525A from Yeti Robotics, and this is our video for the Omaha North Open Tournament. I'm Camden, I'm a sophomore, and I work on every part of this robot, but focus mainly on the software and 3D modeling.
I'm Ryan, I'm a sophomore, and I focus mostly on the mechanics of the robot.
I'm Cole, I'm a freshman. I work on the mechanics and the electrical components. One of our biggest challenges this year is that we made a completely custom built robot, meaning we use no kit-based parts. One downside of that is that we have to wait for shipping if we need any replacement pieces.
So strengths of our robot is being 99% open, using little if not any VEX parts on the robot, and we're quick on the field.
Some improvements we could make on this robot are just working out the bugs and hopefully adding computer vision soon.
So Yeti stands for Youth Engaged in Technology and Innovation. So this summer we did some stuff we went to a summer school and we talked to kids about getting into robots and what they'd be good at when they start.
So we began working on a robot mid-June, and our ideas have changed drastically since then. But we are now happy with our final design.
So, as it was said, this robot is completely custom built. We're not using any VEX metal or anything. We are using 4 VEX wheels and an encoder, but that's about it. So the disadvantage to doing that is we can't just build a robot and see if it works. If that design works, we have to evaluate our planning before actually building the robot. So we made a parts list of absolutely every part of this robot, and then 3D modeled the entire thing except for this lift before we even started building.
When we started planning for the robot and everything, we were joking around about this robot's gonna do 2 cones per second. Well, now that we built the robot and everything, we think and we're gonna try and get to the goal of doing those 2 cones per second during the match.
So there's a rule that states you can only have 1 cone in your possession at any given time during a match. So with a single stage lift, you have to wait for your lift after stacking a cone to come back down in order to pick up another one. So in order to make our robot more efficient, we have a 2-stage robot, so that once a cone is stacked, we can instantly be picking up another one, so we don't lose any time.
So the first stage in this 2-stage lift design is this chain bar, and the belt allows it for this piece to always stay upright, like that. So we press this button once, and it goes directly over a cone, so we can get all lined up. We press again, and it'll bring it up, and we can do this.
So after the chain bar picks up a cone and puts it on our receiver, we have a secondary lift over here that will move over, come down, pick this cone up, move back over, bring it down, and put it onto the mobile base.
So as you can see here, we use a hat to pick up our cones. In order to do so, we have these flaps on the sides of our hat, and they clip on to this top stage of our cone. And then we use this little servo to pull up on the flaps, therefore releasing the cone onto our receiver.
So anything that you see that is blue or white on this robot is 3D printed in a material called PETG, which is the same thing that's in water bottles, and it is strong, but it is also very flexible, and it is our new favorite material. And here are some things that we 3D printed. For example, this is something that holds a bearing onto our mobile goal manipulator, and this is an encoder wheel for a drive that you'll see in a little bit. And we thought a while that we could maybe 3D print Omni wheels, but we ended up not doing that.
So the drive on this robot is a 6-wheel drive, 3 wheels on each side, Omnis on the outside, with a solid 3D printed wheel on the inside, drove by 2 car seat motors, and just belt driven to the outside with 3D printed pulleys. And we have 2 drive encoders on each side with a 3D printed pulley that hooks right up to the belt.
These belts are called XLTP, which means the XL is just the type of tooth profile that they are, and the TP is twin power, so it's on both sides. And an ultimate goal with this robot is to be able to climb out at the field for an extra 20 points. And to do that, this belt will give us a little bit more traction in doing so. And we did all the math for figuring this out knowing the distance between the axles and the size of pulley we wanted.
So underneath, in order to move this around the field with us, I took a 14-inch drawer slide and we direct drove a motor onto a worm gear. We welded a nut onto the top of the drawer slide so that when the worm gear drives, it'll push the mogo out and in with the robot in order to help lift the mogo off the ground and take it with us.
Our brain is powered by an Arduino Mega ADK, and the ADK allows us to have a USB port which we can plug our Xbox dongle into. We have dual motor controllers that each control 2 motors that are really nice. We have a Pololu Mini Maestro that controls several servos with only a few connections to our Arduino. And we have a Raspberry Pi that will eventually be used for computer vision, but right now we're just using it for wireless programming.
So as you can see, we put a lot of time into making our brain look nice and neat, have everything organized, so that when you take everything apart, we know where it is. We put everything on this aluminum sheet here, so that everything can be screwed in and stay organized. In order to hide the majority of our wires, we drilled holes in the plate to route them underneath, so that the majority of the wires are hidden.
So the chain bar, which is our first stage of the lift system, we'll go down, pick the cones up, and to keep the hat linear, so it stays flat, straight up and down on it, we hooked direct down here. We used a GT2 belt from the top to the bottom instead of chain, which is from the original word chain bar.
And then our secondary lift is 3D printed with this same GT2 belt and just bigger pulleys. That is driven by this motor here, and it can rotate like this. There's a servo underneath here, and there's a 3-inch Lazy Susan bearing that we're using, and this whole lift can collapse down.
So in order to collapse it, it's like 12-inch sections-ish, about round there. So we fold down the first one, bring the belt just over. We have the 2 locking pins for the bottom half of the lift that we push in, fold down and over. And that folds all the way down there. So that at the beginning of the match it folds up and out and the belt and everything locks into place so that we're ready for the match and this can move up and down.
So as we were planning our lift, we knew that in order to achieve a tall lift, it had to be collapsible so we could still fit in the box. So as mentioned earlier, we have pistons along 2 joints. Our bottom joint has 2 locking pins to add some stability to our lift so it doesn't flop around as much.
Our notebook is split into a few sections. We have the story of how we got here, which I'll show now. We had a part numbering system where every single part on the robot has an individual part number, and this is how that works. And then we have the details of all these parts on the robot. Next we have all of our handwritten stuff. So this is from late June, and we were originally thinking about doing an X drive, and we actually CAD'd an entire robot but ditched every part of it in the design. This was thinking of ideas of getting out of the field. And then finally at the end we have the code, which is in C++, and we're going for being able to do a command-based system like in FRC.